Welcome back again. Now we'll be discussing a few things that provide some constancy and measure of absoluteness in this world of relativity. So what we'll be talking about today is the space-time interval. Now, before we start talking about space-time, we're just going to talk a little bit about space on its own. Because, as you'd know, even though we've been working on the established assumptions that one of the only real constants in the universe is the speed of light from any frame of reference. Speed of light, or c, from all frames of reference. We just use that because we contract it a little bit, like length. We also know that the distance between two similarly moving objects, or objects stationary relative to each other, we know these things are pretty absolute, right? But if we take this one in particular, not the speed of light, because this has been talked about a bit too much, and we give this bottom one a little bit more attention, we can call it, a distance or a gap in them is an interval, right? And so it follows that there's spaces between objects in space-time. So this is an interval in space. But we're allowed to have intervals, or these set absolute gaps, in space-time. And it kind of establishes that time dilates and length contracts in that ratio or level of proportionality. Because, as we discussed in the other video with the Desmos graph, we showed that there is, in fact, if you take the Lorentz factor, or the relativistic factor, and you remove the multiplication by length, or you remove the multiplication by a change in absolute time, or a change in proper time, you find that the relativistic factor, or the Lorentz factor, is inverses of each other. This is what I'm talking about. 1 minus v squared on c squared. And you have, this is the amount of Lorentz factor by which time dilates, and then on the side here we have 1 minus v, and that's length contracts. That's the amount of the Lorentz factor by which length contracts. So you can see there's a relationship, they're inverses of each other. So it follows that there must be some proportion in a worked example between space and time, respectively, contracting and dilating. So we're about to go over that. Because the distance between two objects moving similarly or stationary relative to each other should be an absolute, or a given. So we start with the photon in a box. This is what I like to call the photon in a box example. So this is a photon moving at speed c, and the box is fixed height h. you're traveling in a rocket. This is rocket A, and you're moving with a velocity of VA. You observe this photon as moving. One moment, I will get a new color. Here, there we go. So you observe this photon as moving like so, where the triangle here is the time it takes for you to pass the photon, which is TA. So this hypotenuse here is the time it takes for you to pass the photon times the speed of light, because it reaches the top of the box here. And if this point is the photon's movement relative to observer A, that means it has reached the top of the box, which means this has to be the fixed height h. And that just makes this LA, or the length of A. And so it follows that h squared plus length of A squared equals CTA squared. Now, I restart the situation, and I rub out our rocket, and I say, okay, well, now that ship A has gone, we have ship B following immediately. Now that ship A is gone, we have ship B following here immediately. So we have ship B. Ship B is a little bit faster than ship A. Ship B moves along with velocity B. Now, it observes similarly, just get a more of a different color. It observes similarly C, like so. It has length B, time B, times the speed of light, because that is, if we have velocity times time, velocity in C, and time times B, we do have distance, and that is the total distance the photon travels. Then we once again have the fixed height h. Now what we can say is, well, h squared plus lb squared equals c tb squared. Now what we've established is, okay, not a lot of things are exactly the same. We have an LB or a TB or a value or variable dependent upon the movement of the object. We have a relativistic variable, but because the photon travels perpendicular, not in the dimension that is contracting, because if, let me just redraw the rocket really quickly. If the rocket travels this way, length only contracts along this line here. The motion of the rocket is dependent only on its vector. It cannot contract length perpendicular. Cannot contract length perpendicular to its motion. So h does not contract. Therefore, h is absolute, because h is the same to the photon in both scenarios. Now what we say is, okay, now we rearrange both to equal h, so we have c ta squared minus la squared equals h. We have c tb squared minus lb squared equals h, and we do these steps by Pythagoras theorem, by the way. Now what we do is we take these two bottom ones and make them equal each other. C ta squared minus la squared equals, or I'll redraw it without the brackets because I have a feeling that you might understand what's going on without them. It's just to keep things neat. C TA, do one bracket around that, squared minus LA squared equals CTB squared minus length traveled by B squared. Now we have a relationship. So we say that there is a perceived absolute between both scenario A and B, which is the height of the box to the photon, because it is not encountered in a direction of travel that is being contracted. And then we can rearrange both Pythagorean equations into an equivalence. And now what we learn is, well, the speed of light is constant in both. The only things different are the time and the lengths. Additionally, we can say that in any given relativistic scenario, we'll just start at the top here. We say in any given relativistic scenario, the value CT squared minus length squared is absolute. It will be the same, regardless of any factors being involved.